Hello and welcome to Unit 3. This is Lesson 1, solving equations using addition and subtraction. Your objective is to solve one-step equations using addition and subtraction. Let's go ahead and jump into it. First thing we need to know is definitions of first inverse operations. Inverse operations are operations that undo each other, such as addition and subtraction. They help you isolate a variable, okay? Isolate means to get a variable by itself or all alone. And again, so addition and subtraction are opposite operations, inverse operations, so they undo each other. Tomorrow, or on the next lesson, we'll talk about multiplication and division being inverse operations as well. Okay, linear equations. Linear equations are equations that have a variable that's raised to the first power. Okay, the variable does not occur in the denominator, under a radical, or inside absolute value symbols. Okay, so let's look at some examples here. Linear equations. X plus 5 equals 9. So if you see, our variable is raised to the first power. It's not squared, okay? It's not cubed. It's just to the first power. So, and it's not in the denominator of a fraction. It's not underneath a radical, which means square root sign. And it's not inside absolute value symbols. Same thing on this one. We've got two variables, but again, they're both raised to the first power. Over here, our x is squared. Okay, so that is not a linear equation, meaning when we graph it, it's not going to be a straight line. It's going to be something else. Then this one, the absolute value one as well. Okay, we can have one that looks like this. This is not linear, okay, or this is also not linear. All right. So again, linear is a variable raised to the first power, and it's not in the denominator, not under radical, not inside absolute value symbols. So that's what linear means. It means when we graph it, it's going to be a straight line. Okay, let's go on to some examples of solving equations. Okay, so here we got three different equations. The first one, x equals negative 17 plus 10. Now remember, the very first, or back when we talked about inverse operations, on that definition it said they're operations that help you isolate the variable. So our goal is to get our variable on a side by itself. Well, if you look here, x is already alone. Okay, so all we have to do is simplify this side. So x equals, and negative 17 plus 10 is negative 7. Okay, so that was pretty easy because x is already by itself. Now, this one here, x minus 5 equals negative 13. Now remember, every subtraction problem we've been changing to addition. So I'm not going to change that for you, okay? I mean, I'm not going to give you different steps. You need to change this to addition. So x plus negative 5 equals negative 13. Now we have to ask ourselves, what is going to undo negative 5? Okay, what's the opposite of negative 5? Well, the opposite of negative 5, or taking away 5, is just adding a positive 5. And if I do that to one side of the equation, okay, I like to draw this little line over my equal sign right here. This is like a wall. If I do this on one side of the wall, I have to do it on the other side of the wall. Remember that property of equality that we talked about? Okay, the property of equality is telling us that I don't change the value of this equation. This side is still equal to this side if I do the same thing to both sides. So I add 5 to both sides. Okay, well, negative 5 and 5, they cancel each other out. That isolates my variable. That's what I want. And negative 13 plus 5 is negative 8. Alright, so let's do one more example here. 3.5 equals n minus 5.5. So again, we're going to rewrite this as an addition problem. So plus negative 5.5. Now again, I want to isolate my n, so I have to ask myself, what's the opposite of negative 5.5? Well, I'm going to add positive 5.5. If I do it to one side of the equal sign, I need to do it to the other side. Okay? Well, negative 5.5 and positive 5.5 cancel. Isolates my variable here. And 3.5 plus 5.5 is 8 2/2, or 9. Now, when you get one that looks like this, I always like to see your n on the left side, and most of you will too, okay, or see your variable on the left side, So I can take this and just flip-flop it around and put n equals 9. Okay, later this unit we're going to do proofs where I will actually have to write on the side why I was able to do that, or it's called a justification. Okay, so later on we'll talk about why I can just flip something around like that. Alright, let's do some more examples. Okay, the directions on this one say to match the real life problem with the equation. Okay, so I need to match these equations right here to one of these problems down here. Well, I'm just going to end up writing the letters underneath the equation that it matches up with. Okay, so A says you have X dollars and your friend repays you the $7 he owes you. You now have $9. How much money did you have originally? Okay, so let's think about this. You have X dollars, so I start with X dollars, and your friend repays you the $7. So that means I'm gaining money, so I should be adding 7. So I'm going to have X dollars plus $7, and that's going to give me $9. So A matches up with the first one. Okay, part B. The temperature was X degrees. It fell 2 degrees and is now 7 degrees. What was the original temperature? Well, if it started at X and it fell 2, that means minus 2 equals 7. So B goes there. Okay, well that means the last one's obviously going to be C, but let's read it anyway. A 9-foot post extends X feet below the ground and 7 feet above the ground. What is the length X buried below the ground? Okay, so if you look at this, we got our 9-foot post. I'm going to take away however many feet are below ground, and that should equal the amount above ground. Okay, so that's C. Okay, we got one more example. Okay, let's do one word problem here because we haven't done one of these in a while. Several record temperature changes have taken place in Spearfish, South Dakota. On January 22nd, 1943, the temperature in Spearfish fell from 54 degrees at 9 a.m. to negative 4 degrees Fahrenheit at 9:27 a.m. How many degrees did the temperature fall? Okay, so verbal model. Well, we're starting with a temperature, so we'll start with our starting temperature. Then it says that the temperature fell, so we're going to take away how many degrees it fell. Degrees fallen, okay? That's going to equal our ending temperature. So the starting temp minus how many degrees the temperature fell equals ending temperature. That should make sense. Alright, so labels. So what do we know here? We know that it's 54 degrees at 9 a.m., so that's the start temp. Start temp equals 54. Okay? We know the end temp was negative 4 degrees, so the end temp is negative 4. And for degrees fallen, we don't know. Okay, so we'll give that a variable. We'll call it x. Okay, so the starting temp is 54, the ending temp is negative 4, and the degrees fallen we don't know, so that's x. Now for the algebraic model down here at the bottom, we plug those labels in place of the words. So instead of starting temp, we're going to put 54. Minus, instead of degrees fallen, we're going to put x. And equals, instead of ending temp, we're going to put negative 4. Okay, well, we got to get this x right here on the side by itself. Okay, so let's change this first. Let's change this to an addition problem. So it's going to be 54 plus negative x equals negative 4. Okay, now let's keep in the back of our minds another way to read this. This is 54 plus the opposite of x equals negative 4. Okay, well, we have to cancel out on the same side as our variable over here, so we have to cancel out this positive 54. We do that with negative 54. Oops, 54. And we get the opposite of x, or negative x, equals, well, negative 4 minus negative 54. Or sorry, minus 54. That's what it should be. Remember, that means plus negative. Same thing. So negative 4 plus negative 54 is negative 58. So I got the opposite of x equals negative 58. Well, we want to know what x is, okay? Because we're trying to figure out the degrees fallen up here, the x. So x If the opposite of x is negative 58, that means that x has to be 58. Okay? So, now we have to answer the question. Always answer the question. It will say the temp fell 58 degrees. So, on these word problems, I'm going to want to see an equation set up. Oops, sorry. An equation set up here. Okay, verbal models are good. You should try to use those. Your book's going to ask for them a lot. Attach labels in place of the words of your verbal model. Then your algebraic model comes from your verbal model. Okay, put together with the labels you got. And then solve the equation and make sure you answer the question. All right, happy homeworking.